So, representing our real numbers. As I said, they can all be placed on the number line, but we can describe them in different ways. Now, the first one is geometrically or visually, by simply drawing a picture of the number line. Algebraically, so we could write an inequation or an equation, depending on what we're talking about, we could do that. We could use a thing called interval notation, as I've put there. Often when we're describing domain and range of functions, we use that notation. Set notation, we could, it's a more formal way of describing the numbers we're talking about. So types of intervals, what sort of intervals can we have? We can have what's called a bounded interval, and that's where an interval has two endpoints. Unbounded will have only one endpoint. Closed means all of the endpoints are included. And open means at least one of the endpoints is not included. And then we have a degenerate, which is just a single point. Right? That's what we call a degenerate. So x is greater than 5. If I put it on a number line, I do it like that. That now brings up a question on setting out. I don't know what your teachers have told you before. Some teachers are paranoid and want that arrow on the line. I never put it on the line. Right? Because you can lose it depending on what colour pen you're using and things like that. Putting it slightly above the line makes it very clear. I mean, don't exaggerate it and be ridiculous. I mean, don't do something like this and go, right, it's this point, and I want all of these ones. Right? So don't be ridiculous about it, but just slightly above so it's very clear what the solution is. That would be an open, unbounded interval. Okay? Endpoints not included, and it only has one endpoint. Interval notation would write it like that. The parentheses we use when the endpoint is not included. Infinity by definition is never included because you can't get to infinity. So you never get there, so how can it be included? And set notation, very similar to the question itself, but we write it that way. And what that says is x such that, so the colon means such that, x such that the x's are greater than 5. Okay, less than or equal to 6 would look like that. That would be a closed unbounded interval. Endpoint is included, only got one endpoint. Okay, when it's included, we use a bracket instead of a parenthesis. X is in between 4 and 6, so we would draw it something like that. That would be an open, endpoint not included, but it's bounded. You got two endpoints there. And we would write it like that. They would both have parentheses, 4, 6, x such that. X is in between 4 and 6. Then we have ones where the endpoints are included. So a closed bounded interval, written like that. And then we have this awkward one, which we just call a bounded interval because it just gets too confusing. So we don't worry about open and closed on that one. We just go bounded. Rational numbers. Anything that can be expressed as a fraction where a and b are integers. They are rational, which brings us to irrational, the other ones, the ones that are not rational. Every irrational number can be expressed as a unique, infinite decimal. Unique. Pi being the most obvious one. It's unique. It never repeats. Never repeats, so therefore it can't be written as a fraction. They think every possible number pattern that exists is inside pi somewhere. That's the belief. Very hard thing to prove, of course, but that is what is believed. Pi is also very good if you want to generate random numbers, because you just pick a string of numbers and go, bang, that's going to be my random set and things like that. Very good for that. We're going to prove that the square root of 2 is irrational. So whilst we don't know the answer, we don't know exactly what it is, we can prove that it is irrational. We can prove that we can't write it as a fraction, and we do it by a thing called proof by contradiction, and that's where you actually assume the opposite of what it is you're trying to prove. So I'm going to assume that actually the square root of 2 is a rational number. Now, if it is a rational number, then I can write it as a fraction where a and b are integers, and they have no common factor. I could simplify them down. Now, if that is true, then b root 2 would be equal to a. Okay? And if I squared both sides, 2b squared would be equal to a squared. All right. Therefore, a squared must be divisible by 2. That's what that's saying. Because remember, b is an integer. And when you square an integer, you get an integer. And a squared's an integer, so it must be divisible by 2. There's its factors. But hang on a sec. In any square, when you break it down to its prime factors, they always appear in pairs. Because you've got to go something times by itself. So if it is divisible by 2, then it is also divisible by 4. Has to be. Therefore, 2b squared is equal to 4 times some integer. Has to be true. So b squared is equal to 2 times an integer. But hang on, a squared is equal to 2 times an integer. Well, that means a squared and b squared have a common factor. Well, that contradicts what I started off with. We said a and b have no common factors. But now I'm saying they have a common factor. Well, that's no good. There's my contradiction, so therefore my assumption must have been incorrect. So I go for the other case. Square root of 2 is not rational. In other words, it is an irrational number. That's a proof by contradiction. Sig figs. Thought we'd talk about significant figures. Remember we had our chat about science teachers and they hate exact numbers and things like that? Because we cannot write down irrational numbers in decimal form. We can write the exact number down, but in things like science, that's not useful. We need to have some sort of an approximation. And we tend to do it one of 2 ways. So many decimal places has done a lot. So many significant figures. Now, writing something to a certain number of decimal places doesn't cause that much confusion. Significant figures sometimes does. So let's look at significant figures. Simple idea. You start at the first non-zero digit and just count the required number and round off same as you would if you were rounding off decimal places. So write these to the correct number of significant figures. If I had 0.050703 and I wanted it to 2 significant figures, I'd start at the 5 and go 1, 2, 0. The next number's a 7, so I round as normal. 0.051 is 2 significant figures. If I wanted to do it to 3, then I'd count it to 7. Next number's a 0, so I'd write it as 0.507. If I wanted it to 4, and actually we write that last 0 down, even though, some look at it and say it's meaningless, but it's not meaningless because it's telling us how many significant figures there are. 3,000. This is the fun one. Write it to 2 significant figures. 3,000. Okay, let's write it to 3 significant figures. 3,000. How about we write it to 4 significant figures? 3,000. You see there's confusion here. Some of the zeros are significant, some of the zeros are holding place value, so you don't change the size. So there's ambiguity. Now, whenever there is ambiguity, use scientific notation. And then that clears up how many significant figures there are. So I wrote 3.0, got to be 2. I wrote 3.00, got to be 3, and so on. Okay? There's a useful thing of scientific notation there if significant figures are important. How about we actually want to work out how many significant figures? Same idea. Start at the first non-zero digit and just count to the end of the number. First non-zero digit there is 5. So 1, 2, 3, 4, 5 significant figures. First non-zero digit there is 1. 5 significant figures. First non-zero digit is also 1, but notice the 0 on the end. We keep counting to the end, so it's now 6 significant figures. 1,200. Okay, 2, 3, 4, I don't know. No way of telling. No way of telling. Is it 2, is it 3, or is it 4? What's holding place value? What is significant? If I get that situation, I'll always write the largest answer. I might not be right, but I can't be wrong. Right? If they were silly enough to ask me that question in an exam, I could not possibly be marked wrong, right? Unless they gave me more information. So I will always go with the biggest number. 4 significant figures. Shakespeare. Or is it?